This is section 4 point, or well, chapter 4, section 4.0. And they finished this off with Cramer's rule. That tends to be kind of at least one of the ultimate um, goals of looking at determinants. Um, so Cramer's rule, it is usually, I would say, of little importance in application as far as actually calculating specific things, numerical things, because it would be heavily computationally intensive. Um, but on the other hand, it's a great theoretical thing. Now, I will say, one time when I was trying to solve a particular optimization problem, I think it was, um, it looked like maybe Cramer's rule might help out a lot in that. Uh, um, I say that it might have. I remember this was years and years ago. I remember kind of going down that path and it helped a little bit, but I kind of got stuck and never got too much further with it and then went on to other things. So I don't even really recall exactly what I was doing, but I do remember I was talking to a colleague about the problem and so forth, and that colleague said, "Well, hey, what about Cramer's rule for And and actually, in that case, it wasn't a bad idea. But generally speaking, this is more. I find it more just kind of a neat theoretical result that uh, is important in that sense. But I wouldn't use it typically to actually try to solve a system of equations. So we have this linear system, a11, x1, and so bring it back to this, but we could always just write this as a matrix equation, um, and down to a n 1 x1 plus all the way over to a, oops, that should have been an n, a n n xn equals bn, and so we have this square system of equations and unknowns, and if the determinant is not zero, okay, so they say if or has a unique solution. Now we already know this part. A unique solution. Oops. If the determinant of A, so determinant of Aij, that matrix made of those components, is not zero. Yeah, we knew that. That came from the previous theorem and previous work and so forth. We better call this delta because we use that. They mentioned that's delta. So we're going to call that determinant delta. Has a unique solution, but in particular, they can tell you what it is in terms of determinants. So x1 is equal to delta 1 over delta. x2 is equal to delta 2 over delta. So we have to learn what these deltas are, and xn equals delta n over delta. So just the delta itself is the determinant of the matrix A, but then the delta I is the determinant of the matrix formed by replacing the ith column with the vector matrix, the single column matrix BJs. Okay, the right hand side. So that's actually kind of amazing, really. So that is just pretty neat, right? So we're saying, hey, if A equals 2, 3, 5, 4, and I would like to solve, well, so we'll say B equals, let's make a solution of maybe 2, -1. So 4 and -3 is 1, 10 and -4 is 6. So I think the solution here is going to be 2 and -1. But so if I have that and I want to solve AX equals B, then what I can tell you is that this answer, x1, is going to equal the determinant of 1, 6, 3, 4 over the determinant of 2, 3, 5, 4. And x2 is equal to the determinant of 2, 5, 1, 6 over the determinant of 2, 3, 5, 4. So you can imagine, right, if I had a 10 by 10 matrix, these would be just really nasty things to do. This would be a terrible way to solve this. But let's kind of check. Let's see what we get here. So x1 is equal to 4 minus 18 divided by 8 minus 15. And x2 is equal to 12 minus 5 divided by 8 minus 15. And so this x1 is what, -14 over -7. And x2 is 7. Try that again. 7 over -7. And we get the solution I thought we would, because I made it that way. 2 and -1. So that's, it's pretty neat. And on this really small situation, it looks like, oh, wow, that is so cool, works so well. But yeah, in the end, that it's not the way you'd want to solve these. There are many better numerical ways to get this done. But that's Cramer's rule. I'm not going to worry about the proof here. The proof is in the text, and I'm not going to go through it again, partly because I think it's great to realize Cramer's rule exists, and it has to do with the cofactor expansion stuff and all that, because we can get a solution that is truly based on both this right-hand side and this thing called the determinant. So that's nice, but again, I am not aware of Cramer's rule really coming up that much. It's just kind of a cool thing to know exists, and I think anybody who takes linear algebra, ought to have seen Cramer's rule. And so there was Cramer's rule. And that, I think, will end chapter 4.